Good evening, Eden community. It is February the 10th, and welcome back to this Thursday's webinar. Theme tonight is correlation versus causality. On with us this evening is Mr. Felix Neguita, who is the head of artificial intelligence for Crypto Data Tech. And we're going to walk everybody through tonight a little discussion on correlation versus causality. I think, as everybody knows, one of the key differences between what we do and what search engines do is related to causality and how we analyze data through causality versus traditional keyword search, which is customary for search engines. So this is the relevance of tonight's topic. We have, again, Felix online with us, who's quite the expert here. He's not only going to provide some introspection and some of his own discussion about correlation, but also take questions at the end of the session, which is customary for our webinar format here. To start, excuse me, I think we'll provide another rundown of the technology that we use, the C+A technology that we use as our data analytics engine, and provide something of a recap of how it works, together with some of its features, and then handing over to Felix for some more technical related discussion. So at the outset, I think everybody here probably is rather well understood that C+8 is the underpinning technology behind Eden and the Knowledge Vault. And what we do versus Google and Yahoo and all these other search engines is we associate data based on causality. So we know, excuse me, that everything that happens is a result of something that's happened before it. And in very short terms, this is how causality works: cause and effect. So what Eden does is we go out into the global data sphere and we capture data. We import that data into our analytics ecosystem. We parse that data, we process that data, we store that data, and then we make it available for queries to the system through knowledge applications that we've spoken at quite some length about, the first of which will be Decision Point. For which will be followed by, as you know, what we have said many, many times, to be loads and loads and loads of knowledge applications for very specific purposes as the future unfolds. So C+8, once we capture it, we take it into our ecosystem, our possession. It becomes a fully autonomous process whereby it's uncontaminated by humans. C+8 is a data importation and transformation engine that allows data to fully self-organize through a complex process of data atomization and systemic association with event causality. So this is a definition that you'll see in various marketing materials that we publish, not least of which is our own website. But for us to sort of encapsulate it in very digestible terms, that's how we say it. The most important factor in providing relevant results and displaying them through its derivative apps, through our knowledge apps, showing how everything is connected to everything else with the help of these simple terms, but instrumental in identifying actionable knowledge, causality, and correlation. So C+8 technology's features, again, to reiterate, we've spoken about this quite a number of times in the past. And again, these are not just features of C+8 technology, but rather some of these are rather disruptive for the field of data science itself. For one, I think everybody knows that there is so much data in the world. We literally don't know how to capitalize on the value that all of this data beholds, largely because there's so much of it, we just simply can't process it all as we speak today. And two, there is so much data that is unstructured in the world. Most of it is unstructured. that prohibits us from being able to put it all into a single space to be able to make accurate analysis against it. So one of C++'s features is that we're able to generalize unstructured data. And I won't say that we're able to do it conclusively in every case, but we are showing the ability to make good progress in this sense, which in and of itself, once achieved, is a massive breakthrough in the field of data science. And again, also by itself would be a freestanding product that would be valuable beyond any knowledge applications we could ever build. Another one of the key features of C++8 technology is the elimination of most human bias in the analytics process. And Felix might touch on this as well, but anybody that understands analysis undertaken by humans will know that most of that analysis, actually, I can probably state more accurately, all of that analysis has some human bias involved. And it's, even where we believe that we're being objective, it is impossible for humans to be completely objective and not pollute analysis, even of the simplest things, with our own bias. So any system or any product that is able to achieve the elimination of human bias in an analytics process is also a significant breakthrough. The third, one of the additional features, third feature, is the ability for data to self-associate. So consider that C++8 was again designed to function, as closely to the function of the human brain as possible. So when Dr. Slower was sitting around over the course of the past 40 years, postulating and pondering how to design a system that would allow humans to use machines to analyze the masses of data that were being created in our world. The design that he ultimately implemented was one that he could most closely associate with the function of the human brain. So when we see a picture, we don't, there's no structured process in our own mind. And, we don't sit there and look at a picture and go, okay, well, that's white and that's black and that's green and it's moving and it's, going up or down or has some certain behavior. It just happens. This data just associates by itself and provides us with some sort of an impulse, some sort of a feeling, some sort of a representation that allows us to then make decisions based on what our senses are providing to us. So the ability to get data to self-associate is another milestone in AI. And ultimately, this is kind of one of the holy grails in our pursuit of artificial intelligence in the field of data science. If we can get data to talk to itself, just like our human brain does, well, I think we can start to imagine how artificial intelligence can begin to replicate human behavior. So allowing machines or designing machines to be able to self-associate data is a major breakthrough. A fourth feature of the C++8 technology is the ability to measure knowledge in a standardizable way. We've talked about this a few times in the past as well. And, there's been a lot of discussion in years past, the last, probably 30, 40 years perhaps, about how data is the new gold. This is a term that we hear and see quite regularly. When we do internet research or we watch people speak in data science forums, so on and so forth. Having the ability to measure knowledge creates a whole lot of other opportunities for us to consider as solutions to problems that remain systemically broken. And I will just table one at this point. And that is, what if, this is another discussion that's been openly had amongst academics and finance industry professionals and experts. What if we could create a currency, some sort of money or medium of exchange that was underpinned by knowledge. Well, most experts will tell you that's a fantastic idea if we could quantify and qualify knowledge, i.e., if we could measure knowledge, right? So the idea with Eden and C+A technology and the knowledge vault is that we will now have the ability to measure knowledge, and we are with the data that we possess. We know we can quantify that knowledge. We know how much we have, and we will always know how much we have. So this starts to give credence to the discussion about pegging some form of a currency in the future to knowledge, which inarguably is man's greatest asset. Gold, for example, which in times past, many currencies in the world were pegged to the dollar under the gold standard. It is no longer the case, but we did this because we were able to measure the amount of gold that was extracted from our planet. So we knew there was a standard, we knew how much gold there was, and we could therefore create currency or money equal to what we had mined in gold from Earth. This has created lots of amazing opportunity for the world. It's allowed the world to evolve at a rate that we have never evolved before. The ability to create money, to create value, sort of mysteriously or mythically, has also caused a considerable amount of problems, not least of which is a debt problem that we are suffering from in the world today that virtually every expert will tell you is going to implode at some point in the not too distant future. So I will, at this point, hand over to Mr. Felix Neguita for some additional discussion on correlation versus causality. Felix?
Thank you, Chris. Thank you so much. Hello, everyone. I'm Felix Neguita, and I'm quite excited to be in front of all of you today. Thank you very much for the invitation. And of course, thank you for the opportunity to speak to the Eden community. So as Chris just mentioned, today we are going to discuss a very interesting subject for me personally as a data guy, as a data scientist, and that is causation and correlation. I hope the Eden community finds this topic quite interesting as well. So on this webinar, we'll have, I hope, productive conversation based on the answers to a few questions related to today's topic. So we're going to get right into it. But first, we need to understand what is causation and what correlation is, as they can seem quite often deceptively similar. Right? So let's start with causation or causality. I will be using these two terms interchangeably. Causation represents the capacity of one variable to influence another, or better said, it is the relation between an event and a second event, where the second event is understood to be a consequence of the first. The first event may bring the second into existence, or may cause some changes in the second event that otherwise would not happen. So I know that maybe this sounds a little bit too abstract, but let's dive into an example as well to clear some of that potential confusion away. So for example, causation explicitly applies to cases where action A causes outcome B. Let us say, for instance, that a 2-year-old is feeling this sensation in her stomach that she later learns is hunger, but for now, she just recognizes that it is something that needs to be addressed, right, immediately. She smells what she later learns is cold food, but now just knows that it is what will make this feeling in her stomach disappear, right, and goes in the direction of the smell. She perhaps enters the kitchen, and follows the smell to a white thing with buttons. The aroma of food is coming from the top of this object. She does not know yet. She reaches up, puts her hand on top of what she later learns is the stove, and unfortunately gets burned. Thus, she learns that the white thing is hot and will hurt you if you touch it. And also that food comes from this strange hot object. So even though the example was quite extensive, its essence is quite simple. If you put your hand on the stove, you'll get burned. We are talking about, in this situation, cause and effect. So the fundamental principle of causality. Now let's talk a little bit about the second term in today's topic, which is correlation. So as many people who work with data for a living know, correlation means association. More precisely, it is a measure of the extent to which two variables are related. There are three possible results of a correlational study: a positive correlation, a negative correlation, or simply no correlation. So a positive correlation is a relationship between two variables in which both variables move in the same direction, right? Therefore, when one variable increases as the other variable increases, or one variable decreases while the other decreases. An example of positive correlation can be represented by measurement references such as height and weight. Taller people tend to be heavier, right? This is the natural tendency. A negative correlation, on the other hand, is a relationship between two variables in which an increase in one variable is associated with a decrease in the other. An example of a negative correlation would be the height above sea level and temperature. So as you climb the mountain, right, you have this increase in height, it gets colder, you have a decrease in temperature. A zero correlation, or as we mentioned before, no correlation, exists when there is no relationship between two variables. So for example, there is no relationship between the amount of the level of tea in a cup and a person's IQ, right, level of intelligence. So why did we choose to have a separate specific webinar about these two concepts? Well, correlation and causation are often confused because the human mind likes to find patterns even when they do not exist. It's almost hardwired into us. We can't help ourselves, right? We often fabricate these patterns when two variables appear to be closely associated, that one is dependent on the other. So that would imply a cause and effect relationship where the dependent event is the result of, let's say, an independent event. However, and this is the tricky part, and this is the vital point of the analysis, we cannot simply assume causation, even if we see two events happening seemingly together before our very eyes. Our observations are purely anecdotal. So there are so many possibilities for an association. In mathematics, there is this common saying, correlation is not causation. And for people who are conducting all sorts of studies, this is sort of like a mantra that they have to repeat to themselves over and over again, right? So the difference between correlation and causation is one of the most important aspects to be mindful of when it comes to statistics, to research, And of course, any respectable analysis based on data, like generally. I believe it would be a good idea to maybe dive deeper into the concept of correlation. So let me try to rephrase what I have been trying to explain earlier. But simply put, correlation describes how two variables move in relation to one another. But what do we mean by movement? And what are these variables? Because I've kept saying variables, variables, variables. So the latter are very easy to understand in the context of tabular data. When you have a table, what our columns represent are the variables, or as we call them sometimes in data engineering, the features. So I propose the following exercise. I have a open source automobile related data set. And I propose, let's take a look at it, get our hands dirty, and do a little bit of coding. So first things first, gods of technology willing, let me try to share my screen so we can dive deeper into this exercise that I have prepared. And I think you should be able to see my screen now. I have this Open Jupyter notebook here. And what I want to do is I want to access this open source data set, and basically together we will be trying to find what's called a correlation matrix. So basically we will be trying to find correlations between variables and try to get our hands dirty a little bit and apply what we have discussed theoretically up until this point. Okay, so first things first. As any software developer knows, I first need to have some libraries that we will be using for today's exercise. Now, I will be coding in Python, but you can do this in pretty much everything. However, Python and R are very good tools for data exploration and data analysis and machine learning. We are using Python quite a lot as a backend language in the Eden ecosystem. So we like it a lot. So let's get started, and I'm going to try to import the libraries that I will be needing. And hopefully I'm not rusty, but I need pandas as a way to get my data together and help me make some operations quicker. You'll see why in a moment. So I'm importing pandas here. Then we also need something to draw a pretty chart. So there is this library called Seaborn that we can import, and it will make us it'll make charts for us. We can see data visualization, which is really cool. And there is another library that we also need for the visualization part. In the case of which, if you've used Seaborn before, you know that there is not really an error, but there are some default settings in it where the charts they're trying to generate are not big enough. So in case we need to make them bigger, I'm going to use another library, which is called matplotlib. And in there's a package I want, which is pyplot. I'm going to be importing these, and I think this is pretty much all we need. So let me just go ahead, run that cell. We can see now that it ran successfully. That's always a good sign. So it's always good when you run your import statements. If it runs, that's great. Awesome. So what do I want to do now? First, we need to bring the data in. Now, the data is open source. It's publicly available at an URL, and we need to read it from there, get it into our little program here. And for that, I'm going to use pandas because pandas has something super cool called data frames. And basically, since I know the data is tabular, right? It's basically a big table. I can read my table as a data frame and then do stuff with it. So I'm just going to declare a variable, right? We call it, let's call it data. It's not very uninspired. Then I'm going to go ahead, use pandas. And from pandas, I'm going to need a function that reads CSV files, because I know that this open source data that I found is in the CSV format. So I'm gonna need the function that's called read underscore CSV. And now what we need to do is we need to pass as an argument here, we need to pass the actual URL path to our data. And that's going to be as a string. So let me paste that in for us. And here you can see that it is an URL and it ends with .csv. So let's go ahead and run that. And it managed to run successfully. Again, we have no problems. So far, at least. Okay, awesome, cool stuff. But the first thing we do when we get any sort of data for any sort of data analysis purpose, for any sort of feature engineering, what we need to do is we want to look at the data with our very own eyes. That's the first thing we need to do, because if we make assumptions, we're going to be wrong about the process, and wrong assumptions lead to wrong results. So let's take a look at it. I can now use this cool data frame that I created with the help of pandas, and there is this head function. And this head function, what it basically does is from our data, it just takes the top 5 rows and it shows them to us exactly for the purpose of simply looking at it, right, with human eyes. So there you go. You run it and we get results. We got 5 rows and we got, you see it says here, 26 columns. And the columns are the things with bold font here. And these are what are called in statistics variables. And in data science and feature engineering, they're called feature. But basically, this is what we mean when we say variables and features. What describes our data? What do all of these numbers or words inside of our data, what do they represent? So something like fuel system, engine size, body style, all that sort of thing, right? So these are our features. And if you remember, from what I've said previously, I've said that correlation describes how 2 variables move in relation to one another. So let's take a look at what we mean by move, right? First off is what we gotta do is it's easier if we find something that is a number. So let's go with engine size. So you see it has these values 130, 130, 152, 109, 136. Cool. But these are just the top 5 rows. Remember, we're just looking at it, right? This is not our entire data set. So what I want now is I want to see all the values that my feature, engine size, can possibly take across our data set. So let's do that. Let's just look at engine size. So let's say data, and then we say engine size. And if we do a dot values, we should get the values. And there we go. We got the values. 130, 130, 152, 109, 136, 136. So these are all the values that this particular feature, engine size, has across our data set, right? However, I wanted to see its movement, which is honestly a bit difficult to see here if they're laid out like this, but since we are cool data scientists, we can arrange what we see here. So let's try to basically take these list of values and arrange them. So let's do something like, I want to see a list of data size dot values. So I can scroll through it now. This is maybe it helps a little bit, but not too much. What I would want to do is I would want to see them from the lowest value to the highest value. So this is good. I'm happy with this, but let's add another statement here where we say that we want them sorted. So if we do sorted list, then if we run it again, there we go, right? So now we have, it starts at 61, then it goes 70, 70, 70, 79, 80, and so on, and it goes up until 326. So basically what we are seeing here is we are seeing that this feature, engine size, can take values from 61 up until 326. So we can say that the value moves, right? The feature moves from 61 to 326. This is what we mean by movement, and this is what we were discussing earlier. So what happens with data sets that are high in complexity is the phenomenon where if one variable moves, so does another, the correlation we've defined earlier. When one variable always moves when another one does, as we have previously mentioned, we say that they are correlated. If they move together in the same direction, you'll recall that we call that a positive correlation, while likewise, if one always increases while the other decreases, that is called a negative correlation. So we can explore that with data visualization techniques, such as correlation matrices, to get a better understanding of our data sets. So let's do that. It's super easy. First off, we would need to actually calculate the correlation matrices for our entire data set. However, if you recall, I said earlier that we can do a lot of cool things with this library called pandas. And one of those cool things is that it can do the calculation for us. So we can have another variable, let's name it core, and we say this is equal to data.core. And what this does is it will calculate a correlation matrix. And as you've seen, nothing appeared here. We know that it ran successfully because there's no asterisk here. However, we got no errors. So again, as I said, that's always a good sign. However, we would like a way to see it. And that's why I imported these two libraries up here, because I wanna take a look at it. And if I want to take a look at it, I also want it to be pretty. So let's do something like, we say that we want our figures. So we do a plt.figures, I think it's figure, no S. And we say we want a fig size equal to 12.9, something like that. We can adjust it if that's not good enough. And then from Seaborn, we want to do something called a heat map. And to do that heat map, we want to pass our correlation object. So that's core. And we gotta say, we gotta define the ticks for the x axis. So that's x tick labels, I believe, is equal to correlation dot columns. And because this is the correlation between the variables in our data set with themselves, right? Because this is what we're interested in. This is going to be also the same for the y tick labels. So it's y tick labels is equal to also correlation dot columns. So we have this matrix that's a squared matrix, right? It's going to be 26 by 26 because I think that's how many we got. Yes, 26. Okay. And let's see if I wrote it correctly, if this does something. Awesome. And it did something. Okay, right. So this is where I wanted to get at. This is the correlation matrix, and this shows us the correlation between every feature we have with themselves. So what happens now is, because these visualization tools are built for the humans to actually look at the data themselves, is we can read this bar here, see which color means a correlation closer to 1, which color means a correlation closer to minus 0.75. So these are strong correlations. So part of the activity of a data scientist or analyst is to read heat maps such as these and charts and interpret them. So on our specific case, a value of 1 means that two variables are perfectly correlated. When when one of them increases or decreases with a certain delta, in the case of -1, the second one does the same with the same delta. So the closer the correlation coefficient, these are also called correlation coefficients, the closer it is to 1 or -1, the stronger the variables are correlated. In our example, we can see, if we take a look at around these kind of shades that we need. So I'm looking at around here, we can see that wheelbase, first off, it has a perfect correlation with itself, obviously. This is why the diagonal is all like this, right? This is called the main diagonal in a matrix. And I'm looking at its correlation with length. So according to this shade right here, the correlation is between 0.75 and 1. So we can say that wheelbase is strongly correlated with length, which obviously in the case of cars, it makes perfect sense. Right. Okay. So now that we got that out of the way, I want to talk about the process for a little bit and some of the things that we need to note, right? So this entire process of discovering correlations in the data set is very important for different other sub-processes, let's say. For example, if we have data sets that are too complex to be parsed in a timely and efficient manner, based on correlations, we can start excluding features in something called dimensionality reduction. So the dimension means the number of features that we have. In the case that I showed you previously, it was 26. So dimensionality reduction means that we need to cut some of the columns out to deal with a smaller data set, basically, because we can't do it in a timely and efficient manner with the larger data set. So we use correlations. If we know that wheelbase is highly correlated with length, we can let one of them go, because we already know that across our data set, if I increase one, the other one's gonna increase the same. So we can exclude one of them from the analysis. And this is called dimensionality reduction. And you may be thinking now, this seems counterintuitive, right? Why would we want to do that? And to give you an example, this is or one of the reasons why I use it, is to help speed up a machine learning training process. So it's very important for artificial intelligence, for machine learning, to be able to parse the input data as efficiently as possible, especially since we have so much data. So dimensionality reduction is some of the things that I do as part of my feature engineering process before we actually go and do machine learning. So that's one example. Now, correlations themselves are also used in various decision-making processes. And since here at Eden, we are in the business of knowledge discovery, we want to talk a little bit more about that. So we need to be very careful when we are trying to understand the world and analyze it based on correlations alone. So how do I say that? Well, first and foremost, we may find correlations between two variables about which we know there is no connection in the real world. And now the question is, to what degree do we let that influence our analysis, basically, at the end of the day? And this is a vital question any data scientist must strive to find answers to. So this is where the jump from raw data to actual knowledge starts to become apparent. So for example, there is this website called Spurious Correlations, which have documented all sorts of funny cases with correlations. And I will also show you, since I shared my screen previously. So if you Google Spurious Correlations, you will 100% get a chance to look at these charts and play with them. And in this example that amused me here, where I was doing research, is you can see that between 1999 and 2009, we can find a strong correlation between the number of people who have drowned in swimming pools, at least I assume it was swimming pools, and the number of movies that actor Nicolas Cage appeared in, right? So they are not perfectly, but they're very strongly correlated. What does this mean? What does all of this mean? Does that actually mean anything for people studying either of the two phenomena? Does it mean for people who are studying how you might drown by falling into a pool? Does this correlation with Nicolas Cage films mean anything? And vice versa, for people who are studying the actor's career, does this correlation with people drowning in swimming pools mean anything? Most certainly not, right? So finding these kind of spurious correlations, or better said, finding correlations that are relevant and significant is a real challenge. And that was my first point. Secondly, we may find correlations if the data set we're analyzing is either too small, so it's small enough that we can, for that tiny piece right there, find the correlation, or vice versa, if it's big enough. If it's big enough, we may find random things that on the span of a wide enough axis, they are correlated. And the reason I'm mentioning this is because we have malicious actors online who frequently use this technique to try to influence public opinion in a certain manner. So this is very well known, and there is great intent behind it and quite well documented. Lastly, and perhaps more importantly, when trying to make decisions based on data, especially forecasting, we must understand that correlation, even though it often becomes, or it often comes because of causation, it does not imply it. This is what I have said previously before we started playing with the code a little bit. And the reason, and this is all, this is also the reason we wanted to talk about these topics today. So, as we would expect, swimming and ice cream consumptions are strongly correlated, for example. They are both caused, however, they're both caused by warm weather. None of the causes, none of them causes either. So it'd be incorrect to assume that swimming always brings ice cream along with it. It may bring consumption of a cold beverage, for example, right? So even though we oversimplify it for the sake of the argument, this distinction is vital because humans are naturally curious. If we have data on some variables, but not others that we know they are in correlation with our own, we will fall into the fallacy of making unbased predictions, right? And the exercise that we did earlier was to show you, to have you see how, let's say, relatively easy it is to discover correlations. I think we did it in, I don't know, 5 minutes or so, but there was, most of it was just me talking about it. But anyone who knows a little bit of Python and a little bit of pandas and mathematics can do it in maybe a minute or two. But while you have seen how easy it is to discover correlations, finding cause and effect chains in this messy real world we live in is incredibly difficult, and it requires hard science. Using data, it is easy to show that smoking correlates strongly with alcoholism. However, we needed years and years of research and medical trials to show that what smoking causes is an increase in the risk of developing lung cancer and not alcoholism. So the question is, how do researchers know when to confidently suspect causation is in play and not correlation? Well, what happens most of the time is one of two things. Either they have a hypothesis to test, and they do so with something called a controlled study, in which basically the data is split into two pools and different modifications are applied to the members of the pool, hoping that it will lead to the observance of statistically significant different results. So, for example, this is what medical trials are actually, and this is what placebo is used for in medical research, right? Or, and this is the fun part and the emphasis that I want to place, they do observational studies. So in this latter case, analysts and researchers look for different behaviors among different groups of actors and try to track the consequences of those behaviors over time. This is something we are trying to give our users the ability to do with the applications we are building. And within our upcoming app, Decision Point, users are already provided with charts for the evolution of the different indicators they are looking at. So let me share my screen a final time, I promise. And I have this prop. I'm not going to be presenting Decision Point because I do not want to steal my colleague Andrei's thunder. That is his gig. But I will be using this cool prop that we have animated. Let me show it to you. So it looks like this. And we have indicators that are going up, down, whatever it is. And our users are also provided with these charts below some of the sections. And as you can see here, this is a time series that they are split by the day to help them track the evolution of these indicators, and hopefully to help them conduct these so-called observational studies. And this is because correlations are already easy to see in a visual first service such as ours. So we want to give our users the ability to as I said, conduct their own observational studies as easily as possible. So by looking at the movement of the indicators in time, we can much more easily test hypotheses about what causes the ones that we are interested in, right? Or whether or not the indicators can be a part of some cause and effect chain regarding other indicators that users might be interested in, like stock price, right? Or a company's momentum, and so on and so forth. So personally, I am very, very excited to see what our users do with it, and how they will be using Decision Point, how it's going to help them, what it will allow them to discover. And I know that I have been talking for quite some time now, and we have promised our community the ability to do a Q&A section, and hopefully I can answer your guys' questions. But I think first and foremost, it's only fair that I let Chris either continue our lovely conversation, or maybe if he has a question of his own, give him the chance to ask. So thank you, everyone. And Chris, right back
Sure,
to you.
Felix, thanks so much, man. Thanks so much. Listen, in view of time constraint, we're going to jump straight into the questions from our community this evening. And I know that we've got some folks online with us. Our trusty colleague, Sarah, has indicated to me that Mr. Ida Pina is on. Ida, are you with us again this evening? Ida, are you in the Zoom meeting with us? Ida, are you plugged in? No, I think Ida, are you there, Ida? Hello? Nope. Okay, Nil, I think we have Nil, Sarah. Nil, you're in the room, aren't you? Nil, can you unmute yourself? Are you here? Sarah, I'll get back to Eaters. Thank you. Nil, I see you're in the room, but hold tight. We're going to move over to Gabriel. Gabriel, are you in with us? And can you unmute yourself, please?
Hi, Chris. Hi, everyone.
Hi, Gabriel.
I'm here. Do you hear me well?
I do indeed, sir. Thank you.
Perfect. So I'll get straight to my idea. I was thinking that understanding human behavior implies generalization and correlation. Yet leveraging the right insights to establish a causality relationship between events involve breaking the linear way of thinking. So my question is, what is the basis on which Eden will know to tell the difference between causation and correlation in its analysis, even when even for a human mind can be confusing?
Awesome stuff. Yes, great question. First of all, hi. Thank you for joining, Gabriel. Thank you for the question. Let's talk about it a little bit. So yeah, you are absolutely right. These kinds of important, what would you say, meta patterns, right? They're meta patterns. They are generalizations. We need to work. We need to be able to generalize, right? From this is part of the difference between deductive and inductive reasoning. So we need to have both these kind of tools at our disposals in our cognitive arsenal. We need to be able to do inductive reasoning, and we need to be able to do deductive reasoning to reach reasonable conclusions about the world. And we need generalizations, because otherwise the world would be a complete chaos that we would be too afraid to even approach. So I agree with you 100%. Now let's get back to the product or ecosystem related part of your question. I think so. So first of all, we are organizing our. We are also organizing our data internally in the backend. We have some quite complex pipelines, right? And at the end of those quite complex pipelines, there is a final step that organizes the data in such a way and to the extent that the decision point application can use it, right? Obviously, it's unable to use raw data. And part of that process and part of that organization is we track the entities that we extract with our NLP process, and we track the actions, and we extract the properties, and we track as they appear in time based on the time of the document that they appeared in. And this maybe is a little bit too technical of an aspect, but it's vital to answer your question. So that is what allows us to build the charts that I've shown in the in my moving prop. And the hope is that because we are trying to make decision point, at least at this stage of development and roadmap of our project, we're trying to make decision point as widely usable as possible. The hope is that you will be able to have this time series, and it doesn't have to be entirely linear, but you'll be able to have this time series evolution or movement to give you the ability to test hypotheses about causation. Maybe it was a bit of a long answer, but this is what I wanted to touch on. So thank you, Gabriel. That was a great question.
Yeah,
Thank
Gabriel.
you for your answer, Felix. To be honest, I'm not entirely sure I followed you, through the whole idea, but I can't wait to see it in practice.
Yeah, me too. Let's keep the conversation going. Gabriel, please reach out to our community, and I'll be more than happy to talk to you more on this subject.
Super, with pleasure.
Gabriel, thanks so
Thank you.
much. Thanks so much.
Yeah.
I think we've got Alexander Maritza on. Alexander, are you with us? Unmute, please, if you're there. Alex?
Yeah, I'm here. I
Hey, pal,
was
how you
not
doing?
able to find the button.
I have
Yeah,
the
so
same problem sometimes.
I will go to the question,
Sure.
and hopefully we'll receive a shorter answer or a more understandable answer for us, which are not working with this every day. So there is my question. Human behavior is in most cases quite predictable for individuals and even more for masses. In this sense, chaos theory can prove itself right when manipulating big data, especially because AI learns from example, right? So, however, being capable of knowing the difference between causality and correlation, is it AI a characteristic or isn't, or is it?
Okay. So first of all, thank you for your question. I think we're on fire tonight, Chris. Thank you for your question. Really appreciate it. It's my kind of questions. I love this kind of train of thoughts. However, you kind of put me on the spot here because you requested a short answer and you mentioned chaos theory. So what am I supposed to do with that, man? Just you gotta help me out. But joke aside, it's not an AI characteristic. I don't know if you followed our event in Dubai. I have mentioned that because people ask me all this, people ask me this question all the time: when will AI replace us? When will AI, so on and so forth. My personal view, and it's not just my personal view, there are a lot of amazing professors out there who share this view, and obviously I do my best to learn from them, is that AI will be another tool in our arsenal. So we will work together with AI rather than against it. AI will be, and it already is, right? We already have it. It's there. You can see it. Is a tool to help you do some of the stuff that you wanted to do. In this case, it's part of the process that builds Decision Point. Decision Point has a lot of AI in it. It's up to you to use Decision Point to see what kind of causations, or if you can find causations in this multi-agent system as chaos theory defines it, right? Now, will AI in and of itself be able to identify cause and effect chains? Maybe this was what you meant. Probably not. And if it will, it's not going to be soon. Why? It is very difficult to, so first of all, to find cause and effect chains. Even for the simpler things in the real world, you need a lot of knowledge of the real world. And it's very difficult to find ways to encode that knowledge so that machines can understand it. Even with the AI we have plugged into Decision Point, we have so much custom stuff built on top of it. It's not just you have data, you put AI in, and that's it. No, it's you have data, you put some AI in, you put some custom algorithms in, you put some frameworks, you put some libraries, you put some other apps, you make some other apps because you don't have what you need. You put a lot of stuff on that until you reach the cherry on top, which is the final product that you guys see. Does that answer your question?
I think so. I think so in a way.
Mm-hmm. Okay, I'll take it.
As I said in the beginning, it's a lot to I don't know, to understand for normal people that are watching and have interest in these kind of things. But until you're not working with them every day, or you're not trying to learn more every day about it, it's quite hard to answer your questions, to understand it.
Mm-hmm. Yeah, I agree, Alex. Until you work with them every day, and until you have some hands-on knowledge, like I said in our coding exercise, until you get your hands dirty, it may be a little difficult for somebody on the outside to get the best understanding they possibly can out of what is happening.
Yeah.
But I really enjoyed your question. Thank you.
Thank you.
Thanks, Alex. Thanks for joining, pal. Thank you. Nil, are you still with us? Nil Sarah. Going once. Nil.
Going once, no.
I think we've lost Nil. Sala, are you still on?
Hello, Chris. I'm on.
Hello, sir. Welcome back. Good to have you.
Hello, Chris. Thank you to have me back. Hello, Felix. I have two questions, actually. To be fair, I want to ask about the data which gathered through the C++8 technology. How to be sure that this data is accurate and reliable? And the most importantly, how to guarantee that the data gathered through the C++8 technology is unbiased?
Mm-hmm. Got it. It's not, and that's fine. So what am I trying to say is, in the context of an analytics tool, which is what Decision Point is, you want to present things as they are out there. For example, we process a lot of news. Why? Because there are studies upon studies that show that there is a statistically significant relevance between what's being said about a certain company and its performance in the open market out there, right? So it's relevant. We know that already, in the literature on that is out, and it's not really debatable. So what you want is you want to see what the people are actually saying and what the people are actually feeling. This is why we have placed so much an emphasis on the social circumflex. And we've talked about it. My colleague Adela, who's our lead social scientist at Eden, she's talked about it in Dubai, and she's talked about this in our webinar series. We want to see what the people are actually saying. We want to see what the people are actually feeling, right? Because they are the open market that you want to refer to. So this is part of you want to capture the subjectivity in it. So there are there is some mathematical, purely unbiased data that you work with, right? Some hard numbers, let's say, and those are available to you, and obviously use them because they're important for, and even we use them in calculating a lot of our indicators. So you have how many employees a company has, right? If we're talking about companies, in how many countries is it located, what's its revenue, what's the stock market price like, so on and so forth, right? These are objective facts. But that's not enough. You need more. You need to see and maybe not measure, but at least represent. Maybe also measure, but let's say represent. Represent what the people are saying and feeling. You want to capture the bias, because otherwise you're missing out.
Exactly.
Does that make sense?
I know exactly what you mean. Yeah, of course. But since the data gathered through artificial intelligence tool, that will help to be unbiased and avoid the human error, or the human biased. That's what I meant.
You meant the process.
Yeah, the process.
Okay, so got it. So here's what's happening. The data, when you gather it, it's not directly plugged into an artificial intelligence. There is an in-between. This will never work. You can't get raw data, plug it into an AI model. It will be garbage because you have garbage in, garbage out. There is a very, very important in between. And this is what people like me do for 90% of their days. It's 10% train machine learning models, make people happy. And it's 90% something called feature engineering. It's a little bit kind of like what we did today. You take a look at it. You have to, as a human, you have to take a look at it. Don't remember that any AI tool, any sort of learning tool whatsoever, even if it learns the features from the data set by itself, it's all orchestrated by humans, right? At the end of the day. So you have to take a look at it. You have to clean it. You have to do principal component analysis and look at correlation matrices like we did today. You have to do dimensionality reduction. You have to do this and that and so many. So there's so many steps in between until you actually have something that is pluggable into an artificial intelligence, right? You don't just collect the data and put it into AI. No, nobody does this. It's not good.
Okay.
It's not gonna work.
Thank you.
Thank you. Thank you for your questions. Great stuff.
Okay, Salah, thanks again for spending the time with us this Thursday night, man. Really appreciate you continuing your support. Felix, we've got one more question that Sarah has asked me to get to. And this is from Eder, who I thought was in the Zoom call with us earlier, but I understand his question came through YouTube.
Okay.
Mr. Pina's question to you this evening is, it seems that the era of correlation is gone. Now is causal inference and reasoning. So the question is, how does C++ tech use machine learning to remove bias and incorporate the how and why relationships?
Okay. I'm not sure how much I agree. I'm not sure how much I agree with the statement that that the era of correlation is over. It's part of statistics. It will never be over. I don't see there's no possible future I can imagine that they were just discarded statistics entirely, right? As a tool in our cognitive arsenal. So not sure what they are referring to there. If it's just like out there, like correlations are not important, that's false. They're 100% important. Now, I see there is this pattern of questions about the relationship between machine learning and bias, and I think it's part of what they wanted to ask. So it's very tricky. I'm not I'm not going to lie, because if you have bias in the input data, your model will basically learn that bias and will continue to perpetrate it. And I think it's the same answer I gave earlier, which is that you have to have somebody prepare all of this input data in advance. So at the end of the day, guys, what's important to remember before we get hyper excited is that any artificial intelligence tool, any machine learning model is a bunch of very complex mathematics behind it, right under the hood. You need to have humans who, with their knowledge of the world, take a look at a data set, see if it's representative, if it's representative for the problem that we're studying, if there is or there isn't bias in it, and eliminate it. And then you plug it into your machine learning. It learns as close to a biasless version of things as possible as it can from the data set you've given it. And then if you have something, if you have a system with something called ensemble learning, which is where you have multiple AIs working together, multiple machine learning models in interconnected pipelines, you can make sure that you remove the bias. But that's something that the system does as a whole, not any particular machine learning algorithm in and of itself. We have to tell the algorithms what the data means to us, right? It doesn't mean anything to the AI. It's just ones and zeros at the end of the day. So I think that's the best I can do as an answer for that question.
Okay, that was Irpina's question, and we are going to take one more from Nil, who has not been able to connect with us in the Zoom call, albeit present with us. Nil's question to you is very simply, Felix, how does Eden manage scalability? In what context, I'm not sure he's asking this question, but I think just generally you can open source a reply here.
Yeah. Okay. So it's how we design our architecture. You have to, when you write any piece of code, you have to make sure that that piece of code is robust, is testable, is maintainable, and last but most importantly, it's scalable. And the same kind of principle applies to the entire system. So the entire backend architecture has to be designed in such a way that it's scalable. So that means how you orchestrate your applications, how they communicate with one another, how you think about your database, and that means you do all the necessary things that you got to do with a database to make it scalable. You have to have load balancing, you have to have sharding, you have to have replica sets, and you have to have all sorts of these things. And then you have to have multiple instances of text parser working at the same time for the exact same purpose of making it scalable. And you have to orchestrate that, and you have to choose the right tools to orchestrate that. And it's a very complex and consuming, let's say, engineering process that I have with our team of software development, of software developers. And it's something that we talk about every day. So whenever we make a decision, we think about how to make it scalable. And the answer is we go and we look at software architectural patterns that can scale. And sometimes we test things out and it doesn't work. And somebody comes to me, somebody comes into my office and says, this takes too long, this is not scalable, this is not gonna work. So we go back and we go back to the drawing board and we think about, okay, how can we code this in a different way? How can we make this, different, and so on and so forth. So the simple answer to how does the Eden ecosystem have scalability is in the software engineering decisions that are dictating the back end of our architecture.
Okay, guys, that's a wrap. Nil, I hope you were able to catch that. Thank you as well for joining. Folks, we're going to wrap tonight. We're 16 minutes past the hour. We tend to be running long these last few weeks, so a few extra bangs for the buck. But listen, again, thanks to the community for extending themselves, for jumping on board with us, for taking the time to learn, stay involved, and support. Again, I'm going to run credits for the production team, starting with Emma, who always sits atop the pedestal, Sarah, Carmen, Cosmin, Thomas, Tudor, who I think is maybe involved again this evening. We've got the crew with us every week here to put this together for everybody, and we thank them yet once again. Folks, we welcome you to join us again next Thursday night, same time, same place, right here on YouTube. Thanks so much. Good night.
Thank you, guys. Good night.
Bye.